Yes. Okay. So let's start finally. So 7 minutes. Sorry. Uh, so today's lecture, I will speak about plain Kolmogorov complexity. So that's the plan for today. So definition simple. So finally, uh, we will give the main definition of the course, like Kolmogorov proposed it in 1965. Basic properties, then I will say that it's not computable. And then there is some kind of side notes, so connection with logic. And don't worry, it's very easy, the connection. I mean, quite easy. Yeah, yeah. So, and we won't need it. So you can sleep if you don't care about it. So then we give some upper bounds. And then a very important property is that Kolmogorov is additive. So information in a string plus information in another string given the first string is equal to the pair. So complexity of pairs. So uh, what is happening? So Kolmogorov was unhappy about probability theory. In 1933, he had this book with the axioms, but he says it doesn't make sense to me. So why he was unhappy? Imagine you have a coin and you throw it many times and it's like the second sequence. It gives 0, 1, 0, 1, 0, 1, 0. So then it is kind of strange. So if person say this is fair coin, or you get only zeros for it for 100 times. So you don't want to believe that this is fair coin. But there was no way in statistics to make such argument. And then he said, what is this? All this probability business. So my axioms are very popular, but nobody starts thinking what is really happening. So, and it's still up today. Nobody cares why they work and what you can express with them. And so he want to answer them. And so people say, yeah, but to get the sequence 0, 1, 0, 1, 0, 1, it's very small probability event to get precisely this sequence. If the length is 100, it's 2 to the power minus 100. But then Kolmogorov says, but the same is true for one that was randomly generated. The probability to get exactly the first sequence. So I took it from atmospheric pressure on random.org. And so the probability to get this first sequence also 2 to the power minus 100. So it doesn't make sense. But then the answer is, okay, but the second one is clearly structured. This has some small structure. So you can print it with small program. Let's say if it continues for 1 million bits, then Python program will just print 0, 1 times 1. Yeah, so it's clearly different. And that was why he introduced Kolmogorov complexity. And he says that the start of statistics should be complexity of finite strings and not the axioms he published in 1933. He said, yeah, okay, they're useful, but it's not, mathematically, it's not the right notion to start thinking from. Okay, but despite his warnings still ignored. I mean, but for good reason, because it's just easy to use the axioms. But warnings also exist for good reason. So that's what we will do today. Okay, so this is some notation, and you already know this for a very long time. So yesterday there was same lecture in Huawei. That's why I have to make the slides, and I will use them today. So what is main idea? We have Turing machines. We view them as programming languages, but also as decompressors. And so let us have some examples of decompressors. So one poor decompressor is one that maps input to the output. So it gives some simple bound. We can try something more clever. So here is a decompressor that looks at the code and then just keeps, so it processes code from left to right. 0 remains 0, but 1 he transforms to 2 ones. And so this code is kind of dictionary that's good for compressing sequences with many more ones than zeros. But it's kind of dangerous code because some sequences, some strings you cannot make with this dictionary. So if there is odd number of ones after each other, you cannot make it. And then compression limit will be infinite. And so here is a better compressor, and that one works well if there are many zeros in the sequence. And so you can form for every word can be has at least one code for the decompressor. And if it has many zeros, then you can create a very small code word. If it has many ones, then first compressor is probably better. So now let's say Kolmogorov complexity is just a minimal compression length for given decompressor. Okay, and so now philosophical discussion. Okay, first some examples. And let me move it. Where can I grab something safely? The more. Okay, so, oops. Yeah, so let's check the definitions. So first line is Kolmogorov complexity for identity compressor M. And this is just, it maps input to the output. So shortest program is just the program itself. So there is a unique shortest program for every string. And so we have 4 and 3. For the decompressor, the second line, it's good for creating one. So if you have 4 ones, we should just repeat the symbol 1 twice. After expansion, we get 4 ones. If we have 3 zeros, then we need to start with 3 zeros. So complexity is 3. And for compressor E, so what do we have there? So easier one is if we have 3 zeros, we can get very short code for it. So was a Kolmogorov complexity of 3 zeros for the last compressor. So it's not clear how compressor works. Yeah, it's 1, because we just need one code word from so the program 0 will print 3 zeros on the right, and to get 4 ones, what should we do? Output. Yeah, we need to start with 8 ones because 2 ones will be mapped to a single one in the decompressor E. So let me go. So here to produce 1, we put 2 ones here, and so if the code word consists of 4 ones, so what we do, we get it's the same. Both D and E work in the same way. So the input word is scanned from left to right, and each time it checks whether there is an input from inputs of sigma. So the code words are 0, 1, 0, and 1, 1. And then when it sees 1, 0, it goes to 0. It appends 0 to the current output. If it sees 1, 1, it appends 1. And so, for example, here you have 1, 0. So it scans the first one. This is the code word. And so it writes 0. Or let's do the right one. So 1, 1. Sigma of 1, 1 is 1. So it writes 1. Then it scans 0, 1. Which is, oh my God. Sorry, that's just 0. Yeah, you're right. So the next code word is 0, and then it prints 3 zeros. Oh, so there is a mistake here. That should be 3 zeros. This 1, triple 0, and then in the end 1. Okay. So here, Kolmogorov complexity is like 1 here, and to get 4 ones, we have to start with 8 ones. Okay. So then let's move to the top. Maybe that's okay. So now after we fix the decompressor, we can at least understand that random sequence will high probability. So for fixed decompressor with high probability, random sequence will be complexity will be at least the length minus something small. Let's say, and why is this? It's just because there are few short programs, and so there are just a few input words that will decompress to a given string. So number of strings of length less than k is this number you see there. So less than 2 to the power k. So if we pick a random n-bit string, then probability that it's smaller than n minus c will be at most 2 to the power n minus c divided by 2 to the power n. So probability to pick n-bit string with small program is 2 to the power minus c at most. Okay, so now we understand that this random string, after we fix decompressor, random string will decompress poorly. And then if we are lucky, our decompressor can compress the structured string. But now that creates a problem. So in order to use this definition, we somehow need to agree on decompressor. How can we do it? And so in general, it's not possible. So you can always say, oh, my favorite decompressor has the top string hard-coded in it. And so so there exists no solution, but there exists almost solution if we think about infinitely many strings. So when we agree to speak about infinitely many strings, then we can do something. But first, let's try to agree with two strings. Okay, so imagine I agree on decompressor, you have one, then we can agree on a compressor together that is almost as good as each of our compressors. So that's what's written here. Kolmogorov complexity of so given D and B compressor, sorry, this R should be F. We construct compressor F that is better than the two others. And so the plan is, so Kolmogorov complexity of our combined compressor is at most one bit more of the best decompressor. And this happens by using the first bit of our code. So the new decompressor will aggregate. It will use the first bit to tell which decompressor we will use. So so that's the plan. So it's like the zip archive works like this. So there is some preamble, and that says, look, there are several decompressors. I will now use this decompressor, and then it's followed by the file that decompresses according to the given decompressor. And so just at the cost of one bit, we can have the best of two decompressors. For example, in previous decompressor, E was good if there are many zeros, and D was good if there are many ones. But D was a dangerous one because some words we could not compress at all. But now we have best of both worlds. We have one that works with many zeros, but the price is just +1 of each code, of each compressed file. Okay, and so we can extend this. And so already explained. So we can speak about prefix-free universal machines. I know we should. No. Okay. Yes, so now we see definition of prefix universal machine. You already use it in the homework, so it is easy to understand. And so it's just a Turing machine that splits the input word into two parts. First part is interpreted as description of another machine. And then on the remaining part, this other machine is simulated. And so example, we already say that Python compiler typically written in C++ or plain C, I don't know. And so if we give it a code together with Python compiler, then C compiler can deal with this. Okay. And so we know that there exists prefix universal machine. I mean, just to prove is how to program Turing machine, long, boring story. Well, okay, it's fun story, but we will not do it. Okay, and then we have to deal with the prefix code. So this was from previous lecture. Okay, and so now let us try to agree on Turing machine. And so let's have a class of machines that are called optimal machines. And that means that Kolmogorov complexity function is smaller for every other machine. Complexity is smaller by at most a constant. So CU is better than any other than any other decompressor up to a constant. And such machine exists because prefix universal machines satisfy a condition. And so the plan is that we will look at the complexity of infinitely many strings and agree that our statements need to be right for optimal machines. So we will make statements that, so if we have two optimal machines, complexity are equal up to a constant. And so this constant, we can never get rid of it unless we have a way to agree on a machine. But it's okay, there are papers like this, but let's not waste time with it. I don't know what's the point, because always people seem to say, no, I don't care about this machine. You have this big model, a complicated definition for what? So let's just not agree on specific machine, but agree on using optimal machines and speak about infinite family of strings. And so in application, we should believe that we work with huge files so that whenever there are compilers, so the files are much bigger than the length of the compilers.
And constant C depends on machine.
Yeah. That's important here. So when we speak about a fixed string, then opponent can say, oh, my machine encodes this fixed string. But he cannot say this for infinitely many strings because machine is finite object, can be given by finite binary description. Okay, and so now we have first property, complexity is bounded by length of the string. So this, of course, this you should remember, it's very easy. And why is it true? So, well, we have this machine that just prints the output, output the input. And for this machine, complexity is exactly equal to the length. So when we change to an optimal machine, complexity increases by at most of 1. So here we have a statement that's true for all optimal machines. So we can drop the constant. Okay. And so again, we can now say that random strings have complexity with high probability, complexity at least length. Again, there is a statement that's true for all optimal machines. So many books, they write the following. I fix one optimal machine, and whenever you see C, you should think about this optimal machine to make sense of the statement. But this is almost the same because machine is fixed arbitrarily. So when I say statement holds makes sense for all optimal machines, then it is okay. So second property, if we have a string X, long string X, and then the second half is the same as the first half. We have a string of the form XX. So complexity is at most X. So how do we prove it? As usual, each time when we prove something, we say this machine does this, and then we have plus of 1 because optimal machine can only be better. So here we have machine that takes a program and just outputs its input twice. And then it's clear, right? Yeah. So then when we go to optimal machine again. So now here a little bit more difficult. So what's the machine for proving this?
The first code will be the each, and then by the function.
Yeah. So it gets a program, evaluates universal Turing machine. So we construct given universal Turing machine, optimal Turing machine here for this complexity. Then we construct a new machine that given program runs optimal machine, then gets the output and applies F to it. Okay. So if the string only contains zeros, then we have a program of length logarithm in the number of zeros. And this is easy. The program is just the number of zeros in binary. So compressor starts printing zeros while counting down the compressor. And so we can define complexity of numbers. I mean, you could also define it as complexity of binary representation. It doesn't matter. It's all the same. Then there is another bound. So it's clear, right? So why is it true? Yeah. So this program, so if we have universal machine here, we take a program of X, and this machine here computes X, then computes the length and erases X. Function C is upper semi-computable. It means we can take a function. Yeah, you know what it means. So we just have a function that prints decreasing estimate. But why is it C is upper semi-computable? So we need a function phi xt. And for increasing t, we need to reach C of x. Therefore, increasing t phi is non-increasing, and yeah,
we can run all Turing machines, and one step B show the best result.
Yeah. That's one way, yeah. So phi of xt, what is it? So we run all programs of length at most x plus constant. Yeah, this constant. And we run them for t steps, and we output the smallest length of a program that prints x. So it's clear. So now question, is C computable? Answer is no, and then there is very paradox. So the smallest number that cannot be described in less than 20 words. So that's 13 words. So if this number is well defined, then you have contradiction because it is description in less than of 13 words. Yeah. So you can, when your friends are drunk, and you can speak about this, and but now you're not drunk, I hope, and so it is clear that there is trap. Okay, so is okay, so here we will use this ID for the proof. So let us I'm going too fast. So let us have function f of n, and it is lexicographic first string that has complexity at least n, more than n. Okay. So f of n is lexicographic first string that has high Kolmogorov complexity, more than n. And so the claim is, so let us now create a contradiction by assuming C is computable. So then the claim is that if C is computable, F is also computable. Why? We just try all the strings in lexicographic order and we wait until one of them is complexity more than N. And so we know there's a small number of small programs. So at some point, okay. And now let us make a chain of inequality. So by definition of F of N is string with big Kolmogorov complexity. So first hold by definition. Now understand F is computable. And we had this thing that applying computable function only decreases Kolmogorov complexity. So this is by our assumption is bounded by C of N, but N is a number, so it's bounded by the logarithm of N. So here we have contradiction. N is bounded by log N. Well, it's contradiction when we choose N big enough. So here the of one constant only depends on the optimal machine here. So for every optimal machine, we can choose N large enough and get the contradiction. So answer for no optimal machine, the Kolmogorov complexity function is computable. Okay. And then, so this really happened in company. So people say we want to push the quality of our compression algorithms. So people, they need to send files. So they have software for cameras and so on, and they want compression algorithm, and they will have researchers that must improve compression algorithms. And they say, can you give us a computable lower bound to check that we are tight against this lower bound? And I say, no, I cannot do this. And they ask me why, and here is proposition. So, and it's for the same reason as this, the proof is almost the same. And so if G is computable lower bound of Kolmogorov complexity, then G is bounded by constant. So why is that? Okay, so let us define F, but now we, instead of complexity, we use the lower bound, the so-called lower bound of complexity. So imagine that G satisfies assumption, G is computable and is lower bound. Then we have precisely the same F construction of G, but with complexity replaced by G. So now the same chain of inequality. So this should be by definition of G. We have that N, sorry, yeah, no, it's right. By definition of F, G of F of N is at least N. And here by assumption on G, so G is lower bound on complexity, so this one is wrong. And then here, F is computable function, so if bounded complexity of value is at most complexity of argument, and then the rest you know. And so there is contradiction. Yeah. Oh, yeah. And then there's a remark. So it's even true if G is lower semi-computable. So not computable, because then we can just wait. So then we have to fiddle a little bit with this definition. So we just wait until on some argument, G of X is larger than N. And then this argument X will be the output. So it might not be the smallest X, but just the first one for which we realize that G is high. Oh, I should not have told this and use it for homework. But yeah, it's okay. I will invent something else. And then, okay, so there is Gödel-Rosser theorem. So Gödel theorem says that that if your logic is even very simple logic, there you can build statements for which there is no proof. this is in most logic courses, this is a very important result. And with Kolmogorov complexity, we can give so they will do this by self-refuting, build a self-refuting statement, a statement that says, I am not provable. But then everyone says, who cares about I'm not provable? And so we will give another statement, complexity of some string is large, and get and prove that this is not provable. So this is, we will give example of Gödel-Russell sentence that's kind of feels more useful. Okay, so but first let's quickly say what is logic. There are just 2 slides about Gödel theorem. So so what is logic? There is an alphabet of mathematical symbols. That's finite alphabet. But then we add also infinite alphabet with variable names. Well, it doesn't need to be infinite, but okay, then but doesn't matter. So we just have infinitely many. We can number them or whatever. Okay, and so then we can make statements like the number 7 is prime. So then you write down 7. So 7 you can write as 1 plus 1 and so on, because there is no symbol 7 in the alphabet, but it's clear how to make it. And then this statement is true if and only if 7 is prime. And so then there is Goldbach conjecture. Okay, I forgot the number. So it should be even number 2n. And so I forgot to write that n is even. So what I wanted to say is n is at least 2, then 2n is not equal to the sum of 2 primes. And I forgot to negate. Okay, it's complete disaster, but you know what I wanted to say. I want to say that the negation of this is conjecture. It's like 2,000 years old or something, and still unproven. And people are kind of hopeless how they can prove that every even number larger than 2 is sum of 2 primes. So yeah, it's a huge mathematical mystery, extremely simple to express in any logic, and no hope for proof. Yeah, it's yeah. So sorry, not 2,000 year, I think, but 400 year. We should check. I will check at some point. Euler. Yeah.
The after of this conjecture is A.
Euler.
Euler.
Yeah.
What
Yeah.
suggested conjecture for 3 sums of 3 primes.
Every number is sum of 3 primes,
And,
larger than, yeah.
For odd numbers, and earlier suggested improved conjecture that still not proven.
Yeah. Yeah.
The funny thing is that I told about this conjecture 5 minutes before this lecture.
You had number theory course, yeah. You gave a talk in number theory course.
Yes, yes.
Yeah. Yeah. I will correct the slides because now you're pretty unhappy about like I wrote the reverse, but okay, so this is also a mathematical statement without proof, but n should be 2n in the right. Okay. So then we say that the statement is provable so logic is not only alphabet with syntactic rules for correct statements, but also third thing, you have axioms and deduction rules. And so then we say that statement is provable if you can start with some axioms, that's just a bunch of mathematical statements that you're allowed to use, and deduction rule transform one statement to other statement. And then the question is there a list of deduction rules that transform axioms to the statement you want to prove? So a statement is provable if there is a list of deduction rules. And so this is interesting because all provable statements, there's enumerable set. Because we can just try all deduction rules and all like brute force all combination of deduction rules and then enumerate all the statements in the end that we have. So we have printer for provable statements. Okay, so that's the only thing we need. So we don't need to know the definition of logic and deduction rule, but I told you anyway, because otherwise it's kind of strange. Okay, and so here is a Rosser extension of Gödel theorem. So Gödel theorem defines talks about true statements, but then I need to tell you what is true mathematical statement. So because I just say here are symbols and deduction rules and what means true. And yeah, and I had a lot of time needed to understand what is true in mathematics. I mean, in the real life, it's okay, but in mathematics, it's different definition. Okay, and so here, Rosser statement, you don't need to understand what is true statement in mathematics. But there is assumption that it only speaks about sufficiently powerful logic. And that means that with this deduction rules, you can simulate Turing machine. So there is a way to store the contents of tape by single natural number. And it's not so surprising because if tape is binary, then we can interpret as number in binary the tape. And so, but making one computation step is just some arithmetic multiplication and division. So you can, it's just a fixed computation. And so it's easy to believe that if your logic can do things with natural numbers, addition, multiplication, and so on, then it can simulate Turing machines. And you can, okay, but this is just, let's not worry about powerful enough. We just say that it can do the things we want with natural numbers. And if it's powerful enough, the logic, then either we can find a statement that can both be proven and disproven. And this is very bad logic if this happens, because if logic is powerful enough, usually it has proof by contradiction. And that means that everything is both true and false. And so logic is useless if it has a proof by contradiction. Or there is a statement that can not be proven and not be disproven. Disproven means that you can prove the not of statement, so negation of the statement. So and this is so there was Hilbert dream, like can you make for every statement either a proof or a negation of the proof? But unfortunately, Gödel proved it was not possible. Okay, and so now let us make a proof of this theorem. So, so first we will look at such statements. So I will say that I give more or less natural example, and we will look to statements that complexity of some string is bigger than n. And so here we will fill in x and n. And so they can be expressed with natural numbers. And in the previous slide, we assumed we have natural numbers, multiplication, and so on. And so what does it mean? So output of machine U on every short program is different from X. And so this we can express with quantifiers. So when we have specific values of X and N, we can specify this with quantifiers. Okay. So we assume logic is powerful enough so that if X has small Kolmogorov complexity, we can always make a proof of it because we just simulate the machine on the program. Okay. Now, if our logic has a statement that can neither be proven nor disproven, we are finished. So when we continue, we assume that second case does not happen. And now we will get that the first case will happen. Well, I don't need to write this. each time I use it, I should say we are okay. So I will remove it from the slides. Okay. So if we find a small n, such that all the strings have complexity at most n, then we can derive contradiction. Because so it's Pigeonhole principle. We have finitely many programs. We can evaluate their output. So if our logical system is enough, then it knows that it can express that for the system of we need a matching between short programs and strings of small complexity. It can prove that matching exists. And so in this case, we have contradiction and we finish. So if all x have a small complexity, then we can derive contradiction. So we can find the statement that's both proven and not proven. So then let's go to the next step. So we know that for all n, we can find at least one x, such that complexity of x is provable. If this is not true, then yeah, okay. So now we will choose some x. For each n, we will choose some x. And we will just so we will look at smallest so for each n, so n is known. So let's take some n, and then let's choose x to be the string for which cx of n has smallest proof. So this is computable function because we can check all proofs for increasing length in the proofs of increasing length and take the smallest one that ends with c of x is bigger than n. So we have computable function, and now we can derive contradiction. So complexity of this string is at most n because n is computable function, f is computable function, and is at most log n. So now we have a proof that f of n has small complexity. But we also have a proof that f of n has large complexity. By definition of f, smallest proof, that smallest x for which c of x bigger than n has proof. Now, this chain of logic, if our logic system is powerful enough, we can transform it into a proof as well. Because we're just bounding out, we're just talking about output of machine. So this computation, and so construction of this machine that gives a small proof, we can evaluate this machine inside the proof system. So we have a proof that c of x is c of f of n is larger than n, and c of n is smaller than log n. And so we derive contradiction. So in other words, if we believe that every statement can be proven or disproven, then we get contradiction. Okay, yeah, that I've already said. So, and this is Gödel proof of Gödel-Rosser theorem with Kolmogorov complexity. And what do we get from this proof? We get that statement that can neither be proven or disproven is of the form, this string has large Kolmogorov complexity. So it says something stronger. There is such a statement that can neither be proven or disproven. And so this feels like more useful than saying, so in the original proof, the statement is, I have no proof. And then everyone said, who cares? That this is, so this weird statement. Okay, so let's now speak about upper bounds on Kolmogorov complexity. Okay. So easy way to get complex upper bound on complexity of numbers. So if two numbers are close to each other, their complexities are also close to each other. So why is it true? So what is the shortest program on N? It just produce shortest program on N and also and compute the difference. And so if the difference you can bound by the logarithm. And so there is a question, why do I write 2 times logarithm instead of 1 times logarithm? And so there is reason for it. And we need to, well, I need marker. So what's happening is that we need to concatenate 2 codes. And then we need to have a way to separate. And so what will be the machine? And so we will consider a machine that receives concatenation of 2 codes. It will be the difference in binary plus the program that prints N. So it will be equal to U of P plus D. And here I need D and prefix-free code. So that I can first separate, drop, I can first move D bar somewhere else and evaluate this machine. And then I extract D from D bar. So that's how machine operates and this rule. Okay. Oh. So second phenomena happens here. So if the complexity of concatenation of 2 strings is complexity of first string plus complexity of last string plus the length, so some code that is needed to separate the 2 programs. And so this machine is not well defined because we don't know where P ends. So when M gets 1 string, it cannot split the 2 programs. So, and then we use prefix-free code, and I will use bar notation for the code we've already seen. And so good proof is we use prefix-free encoding of the length of P followed by P and Q. And then we can use the length to get P. It's easy, right? It's getting boring. So, so now let us define complexity of a list. So what I want to do here is say that to bound complexity of a string, we can bound complexity of a list that contains a string and add logarithmic size of the list. But then I need to say, what is complexity of a list? And this complexity of list is just, we need, the only thing we need to do is encode list as single word. And I do it by just concatenation of all the words. So you can ignore N bar, it's not needed. We just get prefix-free concatenation of many words. And this gives the list. And actually the last word doesn't need to be in prefix-free notation. Okay, but it doesn't matter how we encode the list. So with this definition, it's true that for any X that's an item of the list, complexity of X is bounded by complexity list of 2. And so proof, it's I'm not sure if I wrote it well. Yeah, I think so. And so proof is just concatenate code for list and index. And then expand the list, compute the list, and take this element. So it's clear. Do I need to explain more? Well, actually, I should have asked to tell the proof. That would be faster. Okay. And so now let's look to some special lists. So next theorem uses entropy function, which is very important in data compression. So complexity of X. I made a mistake. That should be like 4 log X. It's a little bit more. 4 log X plus length of X times entropy of the 1 fraction of 1. Okay, so it's clear how to prove. Now I don't say it, and you tell me. So what is list? So the idea is that you use previous result. So what will we use for list? Oh yeah, sorry, there is mathematical result. Yeah. There is combinatorial, so it's not completely ordered. So list will be, so given a number k, list will be the set of all strings with k ones. And so this list is defined by the length of x and the number k of ones. And here is a bound on the length of this list, which is entropy bound. So if it was not seen before in discrete math or something. So here is number of strings with exactly k ones. It is n choose k. And so that's how you calculate this. And then there is famous, like ridiculously precise bound for factorial. It's Stirling bound. Oh, and you learned about, you didn't use it in number theory. Okay, it doesn't matter. So it is something like n to the power n, n over e to the power n divided or multiplied by square root n or something. But for us, all this extra factor and Stirling formula falls out. And we just have this up to actually small constant factor. So there is ratio of square roots here, but it's smaller than 2 or something. I wrote 100 just to be safe because it doesn't matter, or because we have all one constant anyway. Okay, so here we have to add logarithm of size of L. And so this is precisely the logarithm of this thing, and it's precisely entropy function. And so when we take logarithm, we have n over k to the power k and n minus k over n also to the power n minus n. Okay, you can see it faster than I can say it. No? Okay, let
X just a number of one.
yeah, fraction, yeah. So px, we choose this to be k over n. And then we have to take logarithm of this number. So when we take logarithm, we can forget about 100 because we have of 1 precision additive. And so then we just have to think about logarithm of, and here we have 1 over px to the power k. And here we have 1 over 1 minus px to the power n minus k. Okay. And so we can divide by n, and here have n here. So then this n go in the front, and here comes precisely entropy. So this is px, 1 minus px. Okay, it's already clear, so let's not waste time. Yeah, then claim is that when we have optimal compressor, there are always programs on which compressor never prints anything. That has no output. So this theorem from previous slide, and now let's think that decompressor terminates for all of the so optimal compressor is kind of wasting programs because it doesn't print anything on some programs. So it's contradictory. Why not assign something to this program? But the reason is we cannot compute when other programs halt or not. We never know when program is just still thinking or it already it's in an infinite loop or it's just still thinking. Okay, so now we will define a list of programs. So let us have compressor that always halt. And we know that for every length, there is one string whose complexity is at least the length, because number of programs smaller than length is less than 2 to the power length. So we have non-empty list for each length, and we have non-empty list of strings of complexity at least n bit string of them. Okay. And now let's make chain of inequality. So we know that to produce first element of list, we can produce the whole list and then drop all other elements. But to know the list, this list n, it's very easy to compute if we know n. We just take all the programs of length smaller than n. We wait until they're all terminated. Then we have list of strings with small complexity, and the remaining ones, the one n-bit strings that were not enumerated, they have large complexity according to machine. So we know that through Kolmogorov, according to optimal compressor, complexity is log of n. But decompressor says that complexity is at least n. And so D is not optimal decompressor. And so this is the bad news. And actually, so decompressor that achieves this, we can assume it's computable. Because how we build this decompressor, it's just a decompressor that computes the list and only has for each n-bit, only defined on one n-bit string. And precisely this first element of the list. So yeah, so that means that if your decompressor is computable, you are very far from real Kolmogorov complexity, at least on some special strings. So that means if you want to make theory about compressor or decompressor, then you need to make assumption on the data. You need to say, look, this is the most complicated thing, mechanism or structure I care about. Okay. So then we can extend this. So we are now almost finished with part 3 of lecture, upper bounds. But we will use previous theorem in slightly stronger form. So this list, we don't need to compute the whole list and terminate. It's just enough to enumerate a finite list. So the difference is here that we consider enumerable sets, and the program that enumerates the set might never terminate. Before we spoke about a program for list. It prints the list and stops. Now let's generalize and just say we enumerate strings, but maybe program runs forever. But we don't care about this because in the theorem we had we just need to know the index of the enumeration, and it's not needed that program stops after enumerating string x. And so here we will use a family of enumerable sets because our sets need to have finite size. And so if we have family of enumerable sets, then the same proof as before is going through. And here there is another mistake. You see the mistake. So my bound is too good. So it's slightly worse. No, so I concatenated two codes, right? Let's say that if x isn't set as n, so what's our plan? We encode n that we can use to enumerate set, and we append index. The index, so we get a string x, first string, second string, and so on when we enumerate as n. And then this is the index when x appears, the index of x in this enumeration. But I concatenate the code to get this bound. It's not allowed because the compressor doesn't know where. So I need to add 2n or c of n plus log c of n. Okay. Yes, and now we go to very important property, symmetry of information. But first we need to speak about conditional complexity. And so suppose I want, we both have old version of file, there is an update.
Sorry.
Yeah.
Previous slide. Sn is finance.
Yeah.
There is no family sets. Yes, and cannot be infinite.
Yeah, if Sn is infinite, then this bound is infinite and it doesn't mean anything. If for some n we have infinite s, it's not destroying anything. Just then this is useless answer for this x, for elements of this Sn. But note it's uniformly enumerable. I didn't speak about, I kind of skipped it. So what we assume is that so we have a whole list of sets S, and what you want to say is that we can enumerate the table of all the sets. So you have table for each set. We want to enumerate elements. So we want to enumerate the table. We can always extend the row. And that's what means uniformly enumerable. So we have a whole list of sets and we can expand every set.
But there are uniformly enumerable families sets when
All the sets are finite.
Can there be infinite set as n in families?
Yeah, it's allowed that, but then, so we have table and every row is a set. And each time we append elements in S. And so maybe some row, it prints infinitely many Sn. But then for this n, this bound is useless. But maybe for other n, we have finite row and it's still, we can still use it. So then in this case, theorem is still useful. So, but what we need is a single program that enumerates all the rows of the table. That's important. And then the union of all the sets can be infinite. So we still have bound for infinitely many x. And by the way, example of such a set is all strings with Kolmogorov complexity smaller than n. This is example. So let me write. So this is non-trivial example. Sn equal to all x, or let's write sk, c of x smaller than k. No, it doesn't. So every sk is finite. Because we just run all programs of length k in parallel, and each time we find a new one, we add it to sk. And so all this, so you cannot do this with list notation. It's very difficult. And so, so it's equivalent with the halving problem if we need to. Okay, so there's just example. Let's not speak too much about it. Okay. So now last task of this lecture and then some rest. So now the plan is to look at short codes to update some file. You have file, you need to update and so on. And the idea is that to get the updated file, we use the old version. And so here, Y is old version, X is new version. And so complexity of new given old version is minimal program that prints new version. Okay. And now we can again say that there is decompressor that is optimal relative to second argument. And it's for the same reason. So we just construct prefix universal machine that simulates any other machine and it takes second argument into account. We also need to speak about complexity of two strings, X and Y. And that's just by, as we did for lists, by concatenate just any encoding of pairs, for example, prefix free, encoding of first element with second concatenate. And so here are direct properties. Complexity of x given y is at most complexity of x. Complexity of x given x is constant. We just copy the second argument to the output in definition. And if f is computable function, then complexity of f of x and y given y is at most complexity x given y. And so for same reason, we decompress x given y, and then we apply function, but we can recycle second argument. And then the last one, it's also clear, right? So if we have program that uses value of y, then we have program that uses argument, because from argument we complete value and then one program. Okay, so small exercise to get used to conditional complexity. So why is it true? So y is complexity of complexity given string bounded by logarithm of x. And actually it's stupid exercise because we don't need condition x. Because y is the complexity of x is number. And it's number bounded by length of x. So then complexity of number is bounded by logarithm of number. So it's okay. But and this has some consequence. So so this theorem, the proof is a bit difficult, but I put it in the slides for the lecture of yesterday because it's my theorem. I mean, other person made less precise result. So there was some double logarithm here, and then people all the time ask, like, why is it needed? And then I improved the proof. And the corollary of this is that C is not computable. So from this, if C were computable function, then this would be bounded by of 1. Right? Remember from previous, okay, but it's clear, right? Complexity of f of x for computable function is bounded by of 1. Because, yeah. We just consider the machine that evaluates function on second argument, decompressor. So it's other proof that so that complexity is not computable in very strong sense. So it's so there is tight upper and lower bound. Okay. So here is symmetry of information. Complexity of pair is equal to complexity of first element plus complexity of second given first one plus some logarithmic terms. And one direction is very easy to prove. So it's slide. So just by concatenating programs, right? Okay, not for everyone. And there is 1/2 person. So yeah, I know, but other people are looking strange, looking that they do not agree. So okay, sorry, yeah, okay. Then now everyone agrees. Oh, this is just for memory. That's all. As soon as we have a family of enumerable sets, we can use. Here I restate it with conditional complexity. So if we know the number, then we bound it by the logarithm. So almost the same as before. So decompressor is clear, right? It starts to enumerate it has a parameter, then it starts to enumerate all the pairs, X and K, such that X is in K, and then wait until a given index. Okay, and here is the last task for this lecture. So it's the proof that of the other inequality of symmetry of information. Okay, so let us consider 4 things. So there is K, L, and a pair of strings UV. And let us believe that pairs of UV have small complexity. And here I draw the set S with all such strings UV for which complexity is bounded by K plus L. Sorry, I first have to say the statement. So let's fix 4 things, K, L, U, and V. And we will prove that either complexity of U is smaller than K, or complexity of V given U, K, L, and here it should be complexity of U given K and L in the top. Let me write it. C of U given K and L is smaller than K. Plus of 1. And I forgot the of ones as well. So let me write the statement. So either or C and D given U, K, and L smaller than L plus 1. So one of these two we need. Okay. So this claim for fixed U and V. Now let's make a proof and let us create a set S, enumerate that contains all pairs of UV of complexity at most K plus L. And here we have make an access for U, the first elements of the pair, and therefore the second elements of the pair. And now let's look at first elements. We will consider 2 types of first elements. So, we will consider a set of special first elements U, for which there are many V's inside the set S. So it's U section. So we will consider, if U section, so there are 2 types of element U. U section is small and U section is big. Let's first look at U section as small, at most 2 to the power L. Then I claim that first case happens, a second case in the theorem there happens. So we have, if U section is small, then this is true. And why it is? Well, let us enumerate the set SU. It's actually SUKL. We can look to the family of sets of this type. So now it's a triple parameter. So the theorem was with 1 parameter, and now we have 3 parameters, but of course it's the same situation. And then we know that for every X in the set, so for every V in the set, SUKL, we have that this is true. It's just theorem from previous slide. Because we know V by telling the index in the set. We enumerate, if we know UKL, we enumerate the set, and we wait until we see string V. And then the program is just saying the index of V in this enumeration. So this is okay. And this works whenever a U section is small. But what about U section is large? What do we do then? Then the observation is that there are very few such U. So look to the picture. Here is point U with large U section. But there cannot be too many such U because we know size of S is at most 2 to the power K plus L. So we know that size of S bounded by 2 to the power k plus L plus 1. So why is it? Look to the definition of all strings with complexity at most k plus L. So number of U with large section is at most this number divided by, so this size of S divided by 2 to the power L. And this is bounded by 2 to the power k plus 1. And so again, we can enumerate the U that have large U section, because we can enumerate S and then see for every, so check for every U if the large section is big. And so we have proven first inequality. I mean, the correct version is here. So we've proven this one by considering the sets. Let's call them LU. LU is equal to the set of U for which SU is at least 2 to the power now. Okay. So we have both cases. Either U has small SU section, then we have small SU section, then V has small conditional complexity, or it has big SU section, but then complexity of U is small. And in both cases, the claim is true. Okay. And now it just remains to see why this statement in the beginning of the proof implies the lemma. So what do? We set complexity of xy. So set k equal to complexity of x, and set L equal to slightly less than conditional complexity. So a conditional complexity minus a few logarithms. And then we know that second case cannot happen, so first case must happen. And then we set L equal to conditional complexity of y given x. And then we set k smaller than complexity of x minus a few logarithms. And then we know the first case, the other case does not happen. And so then we are finished. And so note that, I forgot to tell, if we have numbers in the condition, so we have complexity of x minus complexity of x given k. Yeah, we don't need absolute value here. Is smaller than 2 log k plus all to 1. So that's I'm also using. If we add number, complexity changes by small amount. And this is again by concatenation. So if we have a program that knows k, that can use k, we can concatenate this program by k and binary and get the program for x. Okay. So that just these numbers there in the condition we can ignore if we just fiddle with k and L by some logarithms. So yeah, I should have pulled first, but okay. Yes. So that's everything for the lecture. Oh, no, one more slide. But it's just a definition. So mutual information. So information of x, information in x about y is complexity of y minus y given x. And information of in x about y is the same as in y about x. So that's symmetry of information, but there is order logarithm term for the correction. So in Shannon entropy, the same exists, but there it's exact up to constant, yeah. But in Kolmogorov complexity, we have logarithmic term, and it's unavoidable, this term. Okay, but first let us see why the corollary is true, and it's written there. So there are two equalities from symmetry of information, and then you arrange them, and then it's the proof is finished. So here in the end of the slide, I prove that it's necessary, this logarithmic term. So if you have string x of length n, then this is equal to c of n minus c of n given x. But x, length of x is n, so this is just c of n. But opposite, c of x minus c of x given n, this is equal to 0, constant if x has large complexity. So what do I know? But we don't need this assumption. Oh, what I'm saying here, c of n minus c of n given x, but n is the length of x, so I don't need this assumption here. It's kind of stupid. And then there is a last question, very common question. If you have, so you can kind of, if you have strings x and y, you can present them in Venn diagram y. And so here is information, and so here is information of y in x. And here is conditional complexity information of x given y, and here y given x. And so when we take, then people say, okay, let's take a program P here of precisely this length that produces x given y, and we do the same here, q here, or let me say y star for easy x star and y star. And then there's a question: can we make a string R such that machine U x star R prints x, and same for y star R equal to y. So note length of x is equal to this complexity and R. And so this is the question: can we have these strings too? Can we actually build such a strings? And so for such strings obviously exist, but finding such R that finish the job does not exist for special x and y. So mutual information cannot be extracted. So this is some tricky property that unfortunately that makes life difficult or interesting, depending of what you want. There also exists mutual information between triples. So if you have 3 strings, you can define mutual information of y and z from inclusion exclusion principle. Cy plus cz minus then complexity of all pairs plus c of yz plus minus plus cx yz. So for 2, we have C approximate definition, Cx plus Cy minus Cxy. And so I forgot to tell. But Cx plus Cy minus Cxy. And so this is approximately up to logarithm. And so we can extend this definition in this way. But there's kind of tricky situation. So then we have Venn diagram with 3 circles. And now we have that this mutual information can be negative. It happens for XOR information. So the XOR, if Z is equal to bitwise XOR of X and Y. So each bit of Z is addition of corresponding bits in X and Y modulo 2. And so what happens if we know Z and X, we can compute Y and vice versa. And so if we take random strings X, Y, Z of length n, then this is 3 times n. but this is 3 times 2n. And this is also, and this is 2n. So what we have is 3n. So we can cancel in this example, 3n minus 4n. So this is a dangerous situation where complexity is negative. And so there are, so situation with 3 strings is tricky, with 4 strings, it's extremely tricky. So it's basically, I don't know about 4 strings, but from some small number on, people have no clue what are possible complexities of tuples. So there's in crypto, and even that it's important for crypto. Okay, it's important for crypto people to understand what are the tuples of complexities, and in channel entropy the same. So there is huge research. Okay. So that's what I mean with one in general cannot extract mutual information. Okay, that's it for this lecture. And so let's have some break. And then there is seminar. I will try to get the seminar printed because I made some updates. So it's restart. You want small or big break? Small break and leave 10 minutes earlier, or a break? Yeah, small break. Okay, then so 7:43 we will 53 we will start, and we leave 7 minutes earlier.